Now that we've talked about differentiating power series, let's talk about integrating power series. Suppose we have the power series representation of a function, n equals 0 to infinity of c sub n times x to the n. Now that we've been through differentiation, integration is going to be considerably easier. Every single one of these terms is going to be using the power rule. You'll notice, however, that I'm leaving a little gap here, and that is on purpose, and I will let you know why. So starting at n equals 0 and going out to infinity, this will be c sub n divided by n plus 1 x to the n plus 1 power. Power of x goes up by 1, we divide by the new power. Now you'll notice, though, that that means that every term would have at least one power of x associated with it. When you take an integral, though, it's necessary for you to include a constant of integration. Now usually this constant of integration corresponds to whatever we get when we integrate this thing. So usually we can solve for c based on the antiderivative of f. Allow me to explain what's going on. We know that 1 over 1 minus x is our quintessential example of our power series. Now, how does this process change if I turn it into 1 over 1 plus x squared? Well, the only thing that's going to need to change is that rather than having x raised to the n power, I can think of this term over here. Sorry, I can't do this without a purple pen. We could think of this right here as 1 minus negative x squared. So this would be negative x squared raised to the n power. Or through the use of, oh, sorry, wrong symbol. God, I'm getting so excited about integrating this power series. Man. So this will be negative 1 raised to the nth power times x raised to the 2n power. Now you may recognize this as one of our common integral forms due to the fact that the function whose derivative is 1 over 1 plus x squared is the arctangent function. So the arctangent of x is going to be the antiderivative of 1 over 1 plus x squared dx, which means that we are going to integrate this power series. Now, as we demonstrated just above, what this means for us, oh, sorry, God, see how excited I am. The power of x is going to go up by 1, and we're going to divide by the new power. So this will give us negative 1 to the n over 2n plus 1 times x raised to the 2n plus 1 power. And of course, there will be a constant of integration associated with this. Now, to solve for this constant of integration, we can use the fact that we know what the arctangent of 0 is. And the reason that I want to use 0 is because that's the center of our power series. It will always converge at its own center. So if we do plug in x equals 0, we'll get the following. The arctangent of 0 is equal to c plus, well, basically every term after this is going to become 0 because they all have x's in them, letting us know that c is equal to 0. Now with that in mind, let's go ahead and identify what happens to the interval of convergence. So like derivatives, the interval of convergence is going to start the same as it was before, but then we need to test the endpoints as well. So let's go ahead and do that. So if we test x equals, let's start with negative 1. Starting with x equals negative 1, we are going to get the sum from n equals 0 to infinity of, reading what I had before, this is negative 1 raised to the n power over 2n plus 1 times negative 1 raised to the 2n plus 1 power. Now, in this case, I'm going to do a little bit of fun algebra here. The fun algebra that I'm going to do is here. I'm going to split this base up at that plus sign and call this negative 1 to the 2n power times negative 1 to the first power. Now this is simply saying negative 1 raised to an even power. Negative 1 raised to any even power is going to be equal to 1 all the time. This negative 1 and this negative 1 are going to go together, and we're going to call this the sum from n equals 0 to infinity of negative 1 raised to the n plus 1 power over 2n plus 1. This is an alternating series. If you apply the alternating series test, you are going to arrive at the fact that this converges. It also lets you know a really fun formula for... Oh, actually, you know what? We'll do that in a sec. This will be more fun. Next, let's test x equals positive 1. For x equals positive 1, we're going to get the sum from n equals 0 to infinity of negative 1 raised to the nth power over 2n plus 1 times 1 raised to the 2n plus 1 power. But 1 raised to any power is simply going to be 1, so we can express this as the sum from n equals 0 to infinity of negative 1 to the nth power over 2n plus 1. Aside from the additional minus sign, this is the exact same series as what we had over here. If you apply the alternating series test, you'll get that this converges as well. Which means that the interval of convergence for this power series representation is now going to be the closed interval from negative 1 to positive 1. Now, that also becomes the domain of our function. Our function was the arctangent of x. Now, what this means is if I plug in x equals 1, I will get the following. The arctangent of 1 is equal to the sum from n equals 0 to infinity of what we got when we plugged in x equals 1. But I know what the arctangent of 1 is. The arctangent of 1 is equal to pi over 4. And according to this formula over here, what that means is that pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 and so forth and so on, which gives us the following representation of pi. Now, I will let you know that with all the math that we just did, we have just proven a value for pi. However, this thing converges so slowly that if you wanted to get, say, 4 decimal places of accuracy on this, you would have to take it out to about 20,000 places. That's right. That's over 9,000